Hey physics classes! Today what I'm going to do is go through some notes on Coulomb's law. I'm going to talk about what Coulomb's law is, show you an equation we can use to calculate the Coulomb force, and then show you 3 examples where we calculate the Coulomb's force or we use Coulomb's law to solve a problem. So first of all, what is Coulomb's law? So we've been talking about electrostatics. And we've talked sort of qualitatively about how you can charge objects so far. You can charge by rubbing 2 objects together and using friction to separate charges. You can charge by conduction of electricity from a charged object to a neutral object. You can charge by induction, by taking a charged object and separating the charges in another neutral object without actually touching it. Now, if we want to talk about quantitative measurements of how charged objects interact, that's where Coulomb's law comes into play. Coulomb's law is going to allow us to measure the electrostatic force between charged objects. Now, if we're talking about a force, we're dealing with something that's measured in newtons. And so if we want to measure that force, the amount of force that is experienced when you put, say, a charged object, Q1, near another charged object, Q2, is going to depend on how much charge is on each of these objects. Is there a whole bunch of positive charge on this one and a whole bunch of positive charge on this one? The amount of charge is important. And so our equation for Coulomb's law involves some constant here. We use K to represent that constant. I'll talk about that one in just a minute. Multiplied by the charge on Q1 times the charge on Q2, all divided by their separation distance squared. So if I know how far apart these 2 objects are, think about the center of this one versus the center of that one. If I can measure that distance, I'll know or I can use this equation to measure the force in newtons. Now, a couple things we need to talk about. This constant K, so let's focus on that one first. So if I want to look at this value right here, that constant K, that's a number, and that number K is basically approximately 9 times 10 to the 9th Newton meters squared per Coulomb squared, are our units. The important thing I want you to know about this K is it's like a scaling factor, like a conversion factor, that helps us use our properties of our problem, the amount of charge here and the charge here and how far apart they are, and allows us to get our force measured in newtons. It's a lot like G in our F equals mg equation. G is the gravitational constant. This letter K is the Coulomb constant that lets us calculate the amount of force that's experienced when you put 2 charged objects near one another. All right, so we got K out of the way. It's a constant. You'll use this number for every calculation you do with Coulomb's law. So the next things we might want to take a look at, we got our 2 charges here. I've got Q1 and Q2. Notice that both charges show up in our equation. So if I want to talk about the force that one object exerts on another, it involves and is important in our calculation how much charge is on each object. It kind of goes along with Newton's 3rd law if you think about it, because the force that object 1 exerts on object 2 should be the same as the force that object 2 exerts on object 1. Notice they both show up here. If I swap their positions and take 2 multiplied by 1, I'll get the same answer as if I take 1 multiplied by 2. Now, when we think about measuring charge, so now we've gone from just describing charge to needing to measure it. Usually, the units that we use to measure charge are coulombs. It's nice, we've got Coulomb's law. Our unit of measure is coulombs. We'll use letter C to measure, to represent that, that measurement. I'm gonna maybe make a little bit more space here. Get those charges out of the way. So our unit of coulombs we use when measuring charge. Coulombs here, and we use symbol C for those. Sometimes, now 1 coulomb of charge is actually quite a lot of charge. And so sometimes we actually see things measured in microcoulombs. And then that would be micro is that little mu symbol. And it looks a lot like it is the symbol we used back when we were working with friction and our friction coefficient. Microcoulombs 10 to the negative is 10 to the negative 6 coulombs. So let me just make a little bit more space here. Get this out of the way because I want to make sure that we recognize that we are looking at microcoulombs here. So 1 microcoulomb is equal to 1 times 10 to the negative 6 coulombs. It's 1/1,000,000th of a coulomb. It's a pretty small value. Now, talking about small values, the elementary charge is a very, very, very small value. It is the amount of charge on 1 proton or electron. It turns out that this is the smallest amount of charge that can exist. So a single proton or a single electron could have that smallest amount of charge is what we call the elementary or smallest charge. Charge is quantized, which means that every charged object has an integer multiple of that smallest possible amount of charge. You can't have half of a proton or a fifth of an electron. You can only have 1 proton, 1 electron, 10 protons, 10 electrons. And so every charged object has a multiple of this amount. So our charge on a single electron, and sometimes we use the symbol E for this, or a single proton, is equal to 1.6 times 10 to the negative 19 coulombs. That's a pretty small number, 10 to the negative 19. This would be our charge on a single proton. I know I'm using the symbol E for that, but often we use E for a proton. And if we're talking about an electron, those are the negatively charged particles. So 1 electron has negative 1.6 times 10 to the negative 19 coulombs of charge. Now this negative sign, it turns out, is important in this because remember, force is a vector. So when I take my Coulomb equation, F equals K, Q1, Q2, all over the distance separating the objects squared. Distance is going to be a positive value. Our constant is going to be a positive value. And so the identities of our charges could be positive or negative. If both charges are positive, our answer for our force value will be a positive number. Whenever we see a positive number for that force, we're thinking this is a repulsive force. It's going to push the charges further away from each other. If we put 2 negative charges in there, we get the same thing. 2 negative charges produce a positive value for force, which means that they repel one another. If, however, one charge is positive and one is negative, then our charge value, our force value that we're going to get is going to have a negative sign in front of it. When we see that negative sign, it means those 2 charges are attracted or pulling towards one another, according to what we see in our calculation. All right, with all that done, let's take a look at some example problems. So, first Coulomb's law example, we're going to have 2 charged objects. Those charged objects have a charge of +1 Coulomb and -1 Coulomb, and they're separated by 1 kilometer. We're going to find the magnitude of the attractive force that either charge is exerting on one another. So we're going to start with our Coulomb force. Our Coulomb force equals K times Q1 times Q2, all divided by the distance separating them squared. So if I'm going to calculate this force, and I want to calculate it in newtons. then when I sub in my numbers here, I want to make sure I use my base SI units. Our constant K is 9 times 10 to the ninth Newton meter squared per Coulomb squared. My first charge here is +1 coulombs. My second charge, -1 coulombs. And in the denominator, I have something that's in kilometers. I'd really like that to be in meters. Notice that in my Coulomb constant that I subbed in here, got meters squared. And so I better make sure that my number that I sub in the denominator in this equation is also in meters. And so right now I have one kilometer, which should be 1,000 meters. And we're going to square that number. Now, you can go ahead and put this into your calculator now. Be careful. Some common errors that I see when we do these sorts of calculations is forgetting to put parentheses when you've got scientific notation. So make sure that you have the parentheses there so you don't say divide or so you divide with what you want to divide by. And another really common error that comes up, I see a lot, is just forgetting to square this thing in the denominator. It's really easy to leave that part off. So I think when you do this calculation, you should find that this force is negative 9,000 newtons. It's actually a pretty large amount of force here. It's a really, really large amount of charge, large force between these objects. Check my math to make sure I didn't make any errors, but I think that's probably what you should see. All right, so let's see. Let's try another one. So the next thing we can do is ask a chemistry question. In the Bohr model of the hydrogen atom, the electron is in a circular orbit around a proton in the nucleus. And here's our radius. That radius is basically how far the proton is away from the electron. We've got a proton, an electron, and in the Bohr model we think about it as orbiting around there. We want to determine the force that the electron is experiencing. Well, in order to think about that Coulomb force, we're going to use our Coulomb force equation. That Coulomb force is K times Q1 times Q2, all divided by the separation distance squared between the two objects. All right, let's fill in what we know. I know, first of all, that this Coulomb constant is 9 times 10 to the ninth Newton meter squared per Coulomb squared. Next, I want to get my two charges. I've got a proton and I've got an electron. The proton in this hydrogen atom is going to have just our elementary charge. It's going to be a positive charge of 1.6 times 10 to the negative 19 coulombs. Every time you have a proton, it has that amount of charge. Every single time. There's no exceptions to that. The electron is also made up of the fundamental charge, but it's a negative value. So anytime you have an electron, its charge is going to be negative 1.6 times 10 to the negative 19 coulombs. We're going to divide by the separation distance between these charged objects. 5.29 times 10 to the negative 11, and that's in meters, and that's squared. All right, so see what you get when you go ahead and do this calculation. Plug it into your calculator. Don't forget to put parentheses here in the denominator, and also to square what you have in the denominator. So I think when you solve this out, you should get negative 8.2 times 10 to the negative 8 newtons, approximately. That negative sign in here is important. That negative sign showed up Because these two objects, this positively charged proton and the negatively charged electron, are attracting one another. They're pulling towards one another. And when we see that negative sign show up in our Coulomb's equation, that's what it's telling us. This is an attractive force between those charged objects. This is a pretty small amount of force, or at least it kind of seems small, 10 to the negative 8 newtons. But don't forget that these are subatomic particles. This is a proton and electron. Their masses are incredibly small. A proton's mass is about 10 to the negative 27 kilograms. So the amount of acceleration it would experience would be ridiculously large given this amount of force on it. However, it doesn't. The electron and the proton don't come crashing into one another. Turns out the Bohr model is just kind of a simplification, and we might get a chance to talk a little bit about some modern physics topics so we can understand that the Bohr model, while pretty good and tells us a lot of things about chemistry, doesn't tell the whole picture about physics. All right, so let's see. And I have one more example for us to do. Third example here. We've got Coulomb's law once again. I've got a 5.1 microcoulomb charge, and it's separated from a negative 3.2 microcoulomb charge by 2.3 millimeters. And we want to find the force between these. Now, the first thing to notice is the values that we have given here. Okay, because remember Coulomb's law, F equals K, Q1, Q2, all over our separation distance squared. And I've got three numbers present, and I know the Coulomb constant already. The Coulomb constant K is 9 times 10 to the 9th